Good afternoon, everyone. In the last class, we have discussed regarding what is sedimentation, what are the different types of sedimentation tank, what are the different types of settling. We have solved the different types of a problem. So we have completed the first part of sedimentation, that is plain sedimentation we have completed, including the problems. In today's class, we are going to see what are the thumb rule. There are some thumb rule in order to keep the design of the sedimentation tank, how much detention time we should keep, how much width we should keep, how much length we should keep for the sedimentation tank. This is nothing but just a thumb rule. For a plain sedimentation tank, the detention time should be 4 to 8 hours. What is detention time? The time period for which the water has to be in the plain sedimentation tank, or in the sedimentation tank, the time period for which the water has to be there in the sedimentation tank. That is, for plain sedimentation, it is 4 to 8. What is plain sedimentation? Plain sedimentation, it is the particle which can be easily settleable without adding the coagulants. That is nothing but the plain sedimentation. Here it is 4 to 8 hours. For coagulation sedimentation, it is in between 2 to 4 hours. Now, plain sedimentation and coagulation sedimentation, you can see the difference. Plain sedimentation is we are giving more amount of detention time, and in the coagulation sedimentation we are giving the less amount of time, that is 2 to 4 hours. Regarding this, why this is more and why this is less, I will tell you regarding this in detail when we are going to discuss regarding coagulation sedimentation. The width we need to keep for the sedimentation tank, that is in between 10 to 12 meters. The length should not be more than 4 to 6 times the width. That means we can keep, if we are going to take 10 meters as a width, then we should keep it as in between 40 to 60 meters. We should not exceed beyond that 40 to 60 meters. So these are the thumb rule for having the sedimentation tank. These are some of the thumb rule for keeping the dimensions of the sedimentation tank. Today's class, we are going to see how to clean the sedimentation tank. For this, what we are going to do is, first of all, while cleaning the sedimentation tank means we want to remove this particular sludge from that sedimentation tank. If we don't remove the sludge, then what will happen? This goes on accumulating and the capacity of the sedimentation tank is going to be get reduced. For that, what we needed to do is we needed to remove this particular sludge. For this particular purpose, what we are going to do is we are going to first fill the water. Then we are, after having this some good amount of sludge that has been settled, what we are going to do is we are going to remove this top water, right? We are going to remove this top water and we are going to keep this particular water till the 30 centimeter depth. This particular water will be too much turbid, it will be having the settled particle in it, it will be too much turbid. This particular water will be having the settled solids along with the water. So what we are going to do is this 30 centimeter water will be consist of the settled particle plus water. So what we are going to do, we are going to remove it with the help of the water. If we are going to, we can use some pump also in order to remove this particular water. But what will happen in pump, due to the settled particle, what will happen, the particle it is going to create a problem for the your pumps. For that, what we can do is we can use the axes, or we can use the buckets. From that buckets we can remove this particular settled sludge, and then we may use pickaxes in order to remove this particular settled sludge. And in the modern modern sedimentation tank, they may use the buckets, and then they may remove this particular sedimentation this settled sludge which is there in the sedimentation tank. And again we can keep, after we can again recirculate the water inside that, and this after 24 hours of the cleaning period. Now the next thing is we need to see regarding the inlet and outlet arrangement, how it should be there for the sedimentation tank. Now you can see the inlet, regarding the inlet part of your sedimentation tank. Here, from here we are going to have the water to be treated inside the sedimentation tank, and this is nothing but called as a baffle wall. Now why we should provide this particular baffle wall? Now if we are directly allowing the water into the sedimentation tank here, what is going to happen is, since the water will be having certain amount of velocity, if imagine there is no baffle wall here, what is going to happen is the water will directly come over here, and it is going to disturb the settled particle. So again what will happen, the water will become continuously, it will be turbid in nature. So in order to prevent the direct entry of the water to be treated into this particular settled sludge, we are going to provide a baffle wall. If we are going to provide the baffle wall, the water will be entering here, and it is not going to disturb the settled particles which are there in the sedimentation tank. So the water, again, the one more reason is the velocity of the water is also, it is going to be get reduced. So the water will come here, and it is going to have the reduced velocity, and with the reduced velocity, what is going to happen, the particle are going to get settled down at the bottom. So this is the purpose of this particular baffle wall. So this is regarding the inlet. Now coming to the outlet arrangement, see, this is nothing but we are having the cut section of your sedimentation tank. This is continuous, the extension of this will be there. When you are going to come to the outlet point, here again near to the outlet point, we are going to have one more baffle wall. Now if this baffle wall is not going to be there, then what will happen, the water which now with the settling with the specific, due to the specific gravity, the particles are going to get settled down here. Now if we don't provide this particular baffle wall, what is going to happen, the water which has to be treated, the water may, if this particular baffle wall is not there, then the turbid water may come out from this particular outlet. Now what is happening is, here the settled particle will be getting settled out here, and the supernant water will be having the relatively clear water, and this relatively clear water we are going to take it from the outlet. So this is the purpose of your again this is we call it as an baffle wall near to the outlet. If we don't provide the baffle wall, again the scouring may happen and the settled particle may come out. For that reason we are going to provide the baffle wall near to the inlet and near to the outlet. This is how the arrangement of the sedimentation tanks will be there, inlet and outlet arrangement of the sedimentation tank will be there. So we have completed the first part of sedimentation, that is the plain sedimentation, types of sedimentation tank, types of settling along with its problem. Now we are going to move towards the coagulation sedimentation process. Now we'll see what is coagulation sedimentation. Now you know what is sedimentation. It is the process of allowing the water to be stand in a sedimentation tank for a specific amount of time, so that the particle which are there in the sedimentation tank, it is going to get settled down by its own weight. Now this is the particle, the plain sedimentation when we are going to have, when the particle can be get settled down by its own weight. Now if the particles are very small with having very less specific gravity, even though we give the specific amount of sedimentation time, the particle will always remain in suspension. Then now the question comes, how to remove such kind of a particle which are not going to get settled down by its own weight. To remove these kind of a particle, we call this particular process as an coagulation sedimentation. Now we should understand what is this particular process of coagulation is, or what is coagulation is. Now these suspended particles, if it is there in the water, it is not going to get settled down by its own weight. In order to settle down, what we need to give, we need to add a certain kind of a chemicals such as alum, chlorinated copperas, like such kind of the chemicals we need to add. Now what these chemicals will do it, now these suspended particles which cannot settle down by its own weight, they are negatively charged, and they are going to have a very less specific gravity. Now when we are going to add this coagulants, what it will do, it is going to have some amount of a charge, the positively it is going to have the positive charge in this particular water, and since these suspended particles are negatively charged in water, what is going to happen when we are going to add the coagulants, it is going to be positively charged. So what is going to happen, this positive and negative, they attracts towards each other and they are going to form the ball like structure, right? When the ball like structure is going to form, we call this particular as a floke, right? We call this particular balls as a floke. When these balls are going to increase in size, what is going to happen, the specific gravity of these particles, of these balls or flokes, is going to get increased. And when the specific gravity is going to increase, what is going to happen, the particles are going to settle down by its own weight, and hence we can easily remove these particles from water. They are going to get settled down here and we can easily remove these suspended particles from water, right? And the process is called as an flocculation or coagulation. I will repeat, the when we add the coagulants, it is going to be positively charged and the impurities are negatively charged. When we are going to add these coagulants, they are going to form the ball like structure, and this is called as a floke, and the floke is going to get settled down at the bottom. Now what is going to happen, the particle is going to increase in size and it can be easily removed. This process is we call it as an coagulation sedimentation, or we call it as an flocculation. We call it as an coagulation sedimentation, or we call it as an flocculation process. Now I was telling why this plain sedimentation is going to take 4 to 8 hours and why this is going to take 2 to 4 hours. See, coagulation sedimentation is going to take 2 to 4 hours. Why is, we are making the particle to get settled down by the coagulation sedimentation process, whereas in the plain sedimentation we are not going to add any kind of a coagulants. We are making the particles to get settled down by its own weight. Since here the ball like structures are getting formed, the specific gravity is getting more increased, right? And then the particle will get settled down very easily, whereas in this case it doesn't happen. So that is the reason why the difference of the detention time will be there in these both the coagulation sedimentation and the plain sedimentation. So I think you have understood what is the coagulation sedimentation. Now we are going to see what are the different kind of coagulants are there for this particular coagulation sedimentation. Now the types of coagulants that we are going to use, that is alum, we call it as an aluminium sulfate, copperas, chlorinated copperas, and sodium aluminate. These are the 4 types of coagulants we are going to use. Now the first one is the alum. We call it as an aluminium sulfate, which having the chemical formula Al2SO4 thrice 18H2O. Now when alum is added into water, right, it is going to react with the bicarbonates which are present in water, and it is going to form the precipitate of aluminium hydroxide precipitate, and it is going to form the calcium sulfate. Now due to this insertion of a calcium sulfate will have the permanent hardness problem in the calcium sulfate, and it is also due to this particular 6CO2. Due to this particular thing, what is going to happen, there is a corrosion problem will be there in these in the water which has to be treated. Now in order to solve this problem, we are going to add the hydrated lime. We are along with this particular the alum, we are going to have an hydrated lime, and it is going to give you the aluminium hydroxide precipitate and C3CaSO4. It is going to be get removed, and then we are going to get the H2O. Now this particular aluminium sulfate is, or alum, it is very it is pH specific. When the pH is going to be in between 6.5 to 8.5, then we can use it, and then the dosage may vary from 5 mg per liter to 85 mg per liter. Now if we want to use this particular alum, we can use the dosage in between 5 mg per liter to 85 mg per liter, depending upon the turbidity of water. Now normally we are going to use the dosage, average normal dosage for the water which has to be treated, we are going to use 17 mg per liter of alum. Now this particular alum is very important, or all these types, the question may come in your exam that explain the different types of a coagulant. The question may come for 10 marks, or they may ask either one of these. They may ask you with the reactions, they may ask one of the type of a coagulant. Now why we are going to use alum in a large scale, or we use alum only as an coagulant? Why is it is very effective as a coagulant, and it is now extensively be used throughout the world. It is available quite cheap and forms an excellent stable flux. The flux, I think you remember what is flux, and it does not require any skilled supervision for handling. This is the main advantage of this particular alum. So we normally use alum as an coagulant. Now the second type is that there is a chlorinated copperas. Now this FeSO4 7H2O, this is called as an copperas. Now when this copperas is going to react with that is chlorine, right, we are going to have the ferric sulfate plus ferric chloride. When this ferric sulfate and ferric chloride, they are more reactive with the hydrated lime. When the hydrated, it is going to react with the hydrated lime, it is going to form the ferric hydroxide precipitate with the release of the calcium sulfate. It is going to form, and when the ferric chloride is going to react with that is the calcium hydroxide, it is going to form the ferric hydroxide precipitate. It is going to get settled down, and it is going to give calcium chloride. This is effective when the pH is in between 3.5 to 6.5. that means when the water is in the acidic range, then we may use this particular water. The ferric sulfate is found effective between pH 4 to 7. Now the next type is copperas. The copperas is we are going to use with the lime. Now when the copperas is reacted with the hydrated lime, we are going to have this ferrous hydroxide precipitate is going to get settled down, and it is going to liberate CaSO4 along with H2O. Now the copperas, when it is going to react with the alkali, that is bicarbonate, calcium bicarbonate, if it is present in water, it is going to form the ferric bicarbonate, and it is going to form the calcium sulfate as a precipitate. Calcium sulfate and ferric bicarbonate is going to form in water. It is going to be, and again it is the ferric hydroxide formed in the earlier case, ferric hydroxide which is formed in the earlier case, it is going to react with this particular water, and it is going to form the ferric hydroxide precipitate. It is going to be removed out. This particular thing is important when the pH of water is more than 8.5 and above. It is more suitable when the water is in the alkaline range. Now the next type is sodium aluminate, which having the formula Na2Al2O4. It is alkaline in reaction, and usually it is less used. Why is because it is more costlier, and it reacts with the salts of calcium and magnesium as follows. It is when the sodium aluminate is going to react with the calcium bicarbonate which is present in water, it is going to form the calcium aluminate, and the calcium chloride and the calcium sulfate, if it is there in water, it is going to form the 2NaCl and Na2SO4. that means more amount of salts are going to get formed. So the sodium aluminate, we are going to use it very rare. Now we will make the comparison between the alum and iron salts as an coagulant. The iron salts will produce more heavy flux and can therefore remove much more amount of suspended particle than alum. Iron salt, being a good oxidizing agent, can remove the hydrogen sulfide and its corresponding taste and odor. Then iron salts can be removed wide range of the pH variable. But now iron salts, when we can use as a coagulant, when we are going to we want to remove the turbidity or color when when the water is in of wastewater kind of a category. Remember, iron salts we are going to use when the water is wastewater and we are going to use an alum when it is a normal raw water. So this is the main comparison between the alum and the iron salts. Now I think you have understood what type of different coagulants. These coagulants, what it is doing, it is going to remove the finer suspended particles. Rather than having the plain sedimentation, it is going to remove these suspended particles in a more rapid way with a very less amount of time. So we are going to remove these kind of coagulants we are going to use. In the next class, we are going to see how to feed these coagulants by having the by different mixing process we are going to see in the next class.